Okay. So last week, the last class, we covered what a derivative was, and this was the formula. And again, if you don't already have that, I put that on your index cards. That's how you find the derivative of a function at any given x value. And another way to say derivative is slope of a tangent line, which I wrote right here, the synonym. So if a question says, what's the derivative? It's pretty much just asking, what's the slope of the tangent line at any given point? And the reason why it's called the derivative, well, this derivative function, we've created a function, we call it the derivative function is because it's been derived from our function. Okay, we've used our function and we're deriving something from it. That's why it was called derivative. Okay, from the limit operation above. So what we're doing today is we've covered what a derivative is and how to calculate it. We're going to be graphing them today. So we know how to find the derivative. Our universal derivative, I think is what I called it. Well, we've created a function out of it. This is going to be called a derivative function, this whole formula right here. And we're going to be graphing derivative functions. So what I mean by that is if I give us a function right here, this is just any old function of this f of x function, we're going to graph the derivative function. What would the derivative graph look like? Okay, so that's what we're going to be doing all the problems today. All right, so I'll try to leave that up if you still want to copy any of it down. But example number 1, it gives us just a random function, and I'm going to go ahead and use a different color. And I want to use this to sketch the graph of the derivative. Now you have two options. You can either use this same graph and graph over the derivative, or if you want, you can draw a separate graph for the derivative. It's up to you, okay? I like to use the same graph, but feel free to make a separate graph if it confuses you having two graphs on one, okay? So here's what the way I start all of these problems by is I look for, I don't even know what to call them properly. I guess you would call them max and mins, but I look for the top of the hills or bottom of the hills. That's probably not a proper way to call it. I guess maximum minimums. I look for those points first and I mark them out. So I found 3 points already. These are like maximum and minimums, or like bottom of the hills or top of the hills. And the reason why I mark these out is because remember, now I'm trying to graph the derivative. My x-axis will be my derivative axis now. And the reason why I mark those out is because at all of these 3 points, I know that the derivative or the slope of these tangent lines will be 0 because the top of the hill just has a flat tangent line. This slope of this tangent line will be 0. Okay, same thing for this bottom of the hill. This slope of this tangent line will also be 0. At all 3 of these points, the slope of those tangent lines will just be a flat horizontal line. And flat horizontal lines have slopes of 0. Okay? And so for that reason, I always start with those points, if there's any. And again, I'm trying to graph the derivative function. Actually, you know what? I'm going to go ahead and, I don't want to confuse you. So let me draw a separate graph for the derivative function, okay? This is now my derivative, okay? The x-axis represents my derivative axis now, okay? Go ahead and erase that. I was going to do it on the same, but it's already starting to get crowded and I'm already losing my head. So, all right, let me go ahead and mark these same points. Here's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So I know that if I'm graphing my derivative, I know that the slope at these 3 points that I've already marked, the derivative will be 0. So I'm going to go to my derivative graph, and at each of those x values, I'm going to mark the derivative as 0. Actually, that's not my derivative axis. I promise you I'm not usually this crazy. It's a crazy day. The y-axis is my derivative axis. Okay. So on this graph, I'm going to go to the x value. I don't know what x value this is. We'll just say that that's, I don't know, 0.5, right? So at the x value 0.5, the derivative will be 0. So that's going to be one of the points on my derivative graph. All right, what about this other point? This is, we'll just say it's about, I don't know, 1.5. So at 1.5, the derivative will be 0. So again, it'll just be on the x-axis. At this other point, we'll say that's 3, right? We'll just kind of round. At this x value 3, the derivative will be 0. So again, that will be another x-intercept or 0 on my derivative graph. So I don't have the full graph yet, but I do know that it's going to have those 3 points. Okay. Let me make this graph bigger. Oh, why did I do that? There you go. Cool. Okay. All right, now what about the rest of the graph? I mean, there's got to be more parts to it. Right now, I only have 3 points marked on this graph, right? Well, let's go ahead and see what's happening between these zeros. So let me go ahead, let me erase all this for a little bit, just so it's not so crowded. Okay. Let me look at what's happening between this x value 1.5 and 2.5 that we've looked at. We've already marked those 2 points right here on the derivative graph. I want to see what's happening between them. Well, if I basically look between that interval, I don't pick any point you want, and try to draw a tangent line to it. Let me pick this point. I try to draw the tangent line to that. It'll look something like that. It'll be a positive slope, right? It's going in a positive direction. If I pick another point, I don't know, let's say this point right here, and I try to draw a tangent line to that, that's also going to have a positive slope. In fact, no matter what point you pick in this interval, from 1.5 to 1.5, all of these points will have positive tangent lines, positive derivatives. So I don't know what's happening specifically between 1.5 and 2, but I know that all the derivatives will be positive, which means they'll be above the x-axis. I don't know why I did it so small. There you go. Okay. And it obviously has to loop back around. The points have to connect. So again, that's why I drew a kind of a curve above the x-axis, because I know they're going to have positive derivatives. Okay. All right, now let's see what's happening. Let's see what's happening between 1.5 and 3. Let's see what's happening between these 2 points. Okay, I'm looking at this interval now. Okay, if I pick any point in this interval, I want to see what kind of derivatives we'll have. Well, if I pick this point, I try to draw a tangent line to it, it's going to have a negative derivative because this tangent line is going in the negative direction. All right, let me pick another point. If I pick, I don't know, this point right here, I try to draw a tangent line to this point. Again, that'll have a negative slope because that tangent line is going in the negative direction. In fact, no matter what point you pick in this interval, all of these points will have negative tangent line slopes. They'll have negative derivatives. They're going in the negative direction. So again, I don't know what's happening specifically, but I know between 1.5 and 3 that the derivatives will be negative. So I'm going to draw a curve underneath the x-axis. The derivative will be negative. So I drew it underneath the x-axis. Okay, and obviously it's got to loop back around. It's got to connect the point. So that's why it looks like a curvy little U. All right, we are almost done. Now we just have to see what's happening after 3, what's happening before 0.5. So let's look at what's happening after the x value 3. What do you guys think is happening on these derivatives? Will these derivatives be positive or negative? Positive, good, because no matter what point you pick, all these derivatives will have a positive, they'll have positive tangent lines. So after the x value 3, just make sure your graph is above the x-axis, okay? Again, these are all rough sketches. Like if you had drawn your graph like that, that's also right. I mean, we're not looking for exact values here. I'm just, make sure it's above the x-axis, okay? That's all you have to look for. And then what about before the x value 0.5? What about this interval right here? Are these positive or negative derivatives? Negative. Let's check. If I pick a point, I try to draw a tangent line. Yep, it does have a negative slope. It's going in the downwards direction. So yeah, negative. So come on, anything before the x value 0.5, it should be negative. Just underneath the x-axis. And there would be a graph of my derivative. Not the cleanest, but you get the point. Okay, it should just have the same general shape. Any questions? Okay, let me go ahead and see how many more. Let me go ahead. We'll do one more just like that, if you didn't catch it. If you're like, I got this, yes.
Is it almost like the inverse of it?
Well, okay, so they're not inverses only because inverses are functions that undo each other. And they're not necessarily undo each other, they are related. I guess I'd call them very, very close cousins is what I'd call them. There's not really, I guess, a mathematical word other than the derivatives. But good question, though. They are related. I wouldn't necessarily say inverse because those are opposite. Now, as far as looking at this graph, I mean, I don't even have it down to where I can just look at this graph and say, oh, the graph's going to look like this right away. I mean, I always have to plot these zeros and then kind of go from there. I mean, if you can, I think that's impressive. Kudos to you. I think that just takes a lot of practice. So, I mean, it is a process. Why did I do that? Okay. All right, let's do another one. If you're like, I got this, feel free to go at your own pace, skip ahead and do them before me. But if not, I'll try to go at a slow pace. So this is just a regular graph. Here's the x-axis, here's the y-axis. And it wants me to draw a sketch of the derivative. So let me go ahead and draw a separate graph. Some people like to do it on the same one, but it gets too crowded, and I don't want to confuse anyone. The x values will mean the same thing, but the y-axis now represents the derivative. Okay. All right. You always want to put room for positive and negative on this y-axis. I tend to forget, but you always should. All right, let's go ahead and start with the top of the hills or bottom of the hills. There's only two of them that I see, and that would be this top of the hill right here, and then this bottom of the hill, because those points have derivatives of 0. The slope of those tangent lines will be 0. So at the x value, we'll say that's about 0.5, and at the x value, we'll say that's about 2. The derivatives will be 0. So let me go ahead and label my axes. Same thing, 0.5, 1, 1.5, 2, 2.5, and 3. Okay. So at 0.5 and also at the x value 2, the derivative will be 0. That's why I marked those points. All right, go ahead and try to finish this one. Try to do the rest of the sketch. I would look at the intervals now, see what's happening between 0.5 and 2, see what type of derivative that has, positive or negative, and try to draw a sketch of it, okay? If you're stuck, I'll walk around and help you. And we'll go over together. Just want to see if you can try to figure the rest of this one out on your own. You're done. Feel free to look at your partner's paper and see if those pictures kind of look the same. If you're near someone, please just check that your picture matches with at least one person.
She's in class or she's outside?
Okay. All right, I saw a lot of right pictures. Your picture should have looked something like this. Between 0.5 and 2, the derivative is negative, so just kind of maybe like a U underneath the x-axis. After the x value 2, it's positive. And before the x value 0.5, there's only a small increment to look at, this little increment right here. But those are positive derivatives as well, positive tangent lines. So basically, it kind of looks like a parabola. Kind of wonky parabola, but it should look something like that. Okay. And again, if your graph maybe look like maybe your graph looked like this. Let me see. Okay, that's also technically right. I mean, we're not being specific on the actual numerical values and points. Just the general shape is fine. Okay. As long as you have the positives above the x-axis and the negative derivatives below the x-axis, you should be fine. That's all I'm going to look at. Okay, let's move on to the next page. On the next page, illustrate this form by comparing graphs to f of prime. I think we'll probably skip that one just for the sake of time. I want to leave more time for the review, but that's something we've done. It's just another example. You can sketch that graph and then sketch the derivative. All right, I'm going to go ahead and move on to this is the second page still. And these are just other notations that you might see for derivative. Now, I don't know why. There's like about 10 different ways to say derivative in math form, and I don't know why. There just is, okay? The most common way that you'll see is f prime of x. When you see that, that means the derivative of f of x, okay? Find the derivative of the function f of x. You might also see the denotation y prime. That also means derivative. You might see, I don't really use dy dx a lot, but that's another way to say derivative. And in fact, it means the derivative of y with respect to x. That's technically what it means, okay? I never see this one, that's for sure, but I mean, I guess that you could also see that one. This one, you might see the derivative of this function f of x with respect to x, meaning x is the variable they're going to use. I don't see these other two at the end. I think I saw them maybe like in calculus 2 or 3 with a different professor, but I only highlighted the ones that I use or that you'll see in this class at least. But those are other ways. They all mean the same thing. They're just different ways to write, hey, this is the derivative of something. Okay? All right, we've been talking a lot about derivatives, and now we know how to graph derivatives, the graph of a derivative. Now, I do want to cover a few special cases on when derivatives maybe won't exist. Okay, when will we not have a derivative? Okay, and there's actually 3 cases in which this happens. I've listed all 3 of them below. When will a function not have a derivative? When will a function not be differentiable? Differentiable means it has a derivative. Okay, so when will it not have a derivative? Well, there's going to be 3 times when a function doesn't have a derivative. Okay, keyword. 3 times when the function doesn't have a derivative, when it's not differentiable. The first case is whenever there's a corner point. Okay, maybe there's a sharp corner. It's okay for it to have a bunch of rounds, curvy edges, but if there's a sharp corner, such as, that sharp corner, then there won't be a derivative at that point. You won't be able to calculate the derivative, the slope of the tangent line at that point. And the reason why is because if you have a curvy point like that, I mean, you could have this line as the derivative, the slope of that tangent line, but you could also draw it another way. You could also draw, this tangent line. That's technically a tangent line. And that's why there's not a unique tangent line in those cases. There's no derivative because there's so many different ways to draw a tangent line. So that's one case in which you won't have a derivative, is at a corner point like that. Yes?
And so if there's no derivative, will we just put it does not exist?
At that point, yes. So there's a derivative for this point, there's a derivative for this point. I can go ahead and find the slope of that tangent line. But at that specific point, at this a value, you would say it doesn't exist. Okay. Another time when you won't have a derivative is at a discontinuity. So let's say maybe your graph is broken. So you have this graph and everything's fine, but then you have a jump from one place to the other. And the question's asking you, what's the derivative at this x value? Well, there's no derivative because there's the jump. I mean, there's really, the left and right side of the limit don't match, right? So you won't have a derivative at any discontinuities, any jumps. Okay. And then the last case, this one's not common. I don't think I've ever really seen it up here. I didn't put it on a test or anything, is whenever there's a vertical tangent. So for example, if your graph, was this curvy line, everything's fine and dandy, but then the graph just kind of is a straight vertical line for an instant, at the vertical straight part, I guess the derivative wouldn't exist because it's a vertical line. But again, that one's really not that common. You won't see it on a test or anything. And I don't think even I put that one on a homework, so. But it does exist. Okay. But yeah, those are the only times where a derivative won't exist. Everything else, there'll always be a derivative. There'll always be some slope of a tangent line. All right, let's go ahead and do an example on what I mean by that, and then we'll end with example 5. So example 4, where is this function f of x equals the absolute value of x differentiable? Now, if you have a graphing calculator, feel free to sketch that. If not, I'll just tell you what the graph looks like. Here's the x-axis, here's the y-axis. And if you graph this line, f of x equals absolute value of x, it just looks like, it looks like that. Now, based on the 3 cases I just told you, at what x value, it's not the perfect picture, but you get the point, what x value does this graph not have a derivative? At x is 0. Thank you. At this point right here, at the corner point, because it's a corner point. So this function is differentiable everywhere except at 0. So I guess I would say that. This function has a derivative everywhere. You could say it has a derivative, or you could say is differentiable. Same thing. Differentiable everywhere except at the corner point, which is at the x value 0. Okay, it doesn't have a derivative at that point because it's a corner point. And that's all you would say. Okay. Okay. All right. We'll end up with example number 5, and then we'll move on to the review. So again, like I said, pretty short day. It's not so bad. Example number 5, higher order derivatives, and we'll do more of these higher orders in the weeks to come. So this is just a small preview of what a higher order derivative is. So let's say you have a function, I don't know, x to the third power, f of x equals x to the third minus x. And you wanted to find and interpret, and this is pretty important, so let me zoom in on this. F, and then there's 2 apostrophes. Now remember what I said earlier, f prime of x, that's how you would read it. F prime of x means the derivative of a function. So I don't know what the derivative is. Actually, I'll just show you what the answer is. It is 3x squared minus 1, okay? And if you're wondering how did I got that, feel free to use the whole limit as h approaches 0 of f of x plus h, you know, the whole thing, okay? But that's not the point I'm trying to get at, okay? So that, let's say that's our derivative. And the question asked you to find, notice that there's now 2 apostrophes. Now the way you would actually read that is f double prime is how I would read it. You might also hear the second derivative. There's 2 apostrophes because it means the second derivative. You know the first derivative, you know the derivative is 3x squared minus 1. I mean, I just told you that. But if you wanted to find the second derivative, that just means you would find the derivative of the first derivative. That's what that means, okay? And again, I mostly read it as f double prime, but you can also just say the second derivative of this function f of x. The derivative, you would find the derivative of the first derivative. So I'll go ahead and do this example. Let me just write this out first. Okay. So if I wanted to find the derivative of 3x squared minus 1, again, I would use the formula. Now, for those of you that know the power rule, again, we'll be doing that in the coming weeks. We haven't learned that yet, at least not the rest of the class. So I'm going to go ahead and just use this formula up on top to find the derivative of something. The limit as h approaches 0, all that. So let me just rewrite that at the bottom of this page. The limit, right over here. The limit as h approaches 0 of f of x plus h, or f of a plus h, either one, minus f of x over h, okay? All right, now I'm going to take the derivative of the derivative. I'm not worried about the original function. I'm worried about my previous answer. So I'm going to go ahead and let me just plug this in to my previous answer. So I'll have, this is going to equal the limit as h approaches 0 of, and then f of x plus h, that just means you're going to take your function, and everywhere you see an x, you replace it with x plus h. So we'll have, let me use brackets, 3. Instead of x, I'm going to have x plus h squared instead, minus 1. Okay. Minus, and then it says minus f of x, that's just your function f of x. Now, again, it's a little confusing because it's like, hey, f of x is up here, but again, we're taking the derivative of the first derivative. So my f of x is this derivative in this case. Minus 3x squared minus 1, and the whole thing is over h. Okay. And then you would just simplify. Obviously, you can't direct substitute 0 in for h right away because you would get an undefined denominator. So you'd have to do some of the algebra and simplify that. So let me see what I get. The limit as h approaches 0. And on the numerator, let's see, we get 3. And you can FOIL this out, x plus h squared. You should get x squared plus 2xh plus h squared. I just FOILed out the x plus h squared. Minus 1. Minus, I'm going to go ahead and FOIL that minus sign to both things in the parentheses. So minus 3x squared and minus negative 1 will turn to a plus 1. Because I FOILed that negative to both terms on the inside of the parentheses. And the whole thing is over h. All right, we can go ahead and simplify this a little bit more by distributing that 3 outside the parentheses to everything inside the parentheses. So let's see, once we do that, we'll have a numerator of 3x squared. 3 times 2 is 6xh. 3 times h squared is 3h squared. Minus 1 minus 3x plus 1. And the whole thing is over h. All right, now there's going to be some terms that cancel out. Let's see what cancels out on the numerator. Let's see, we have A -1 and a +1, those cancel out. Is that it? Usually more cancels out. Always makes me happy when stuff cancels out, but I think that's all. Okay, I guess that's it. Well, that's a
You didn't carry down the squared.
Oh, hold on.
3x squared, so that depends on.
Oh, nice catch. Yes, thank you. Don't tell me. Not Megan, because I called you that. Don't tell me.
Starts with a K.
Kylie Quinn, right? I got the last name too. Okay, cool. Thank you, Kylie. Yes, I am going to carry down that a squared power. And you caught a mistake that I made. So anytime you catch a mistake, you get an extra like 2 points on the exam. So you remind me if I don't give it to you. Okay. All right. So yes, the 3x squareds cancel out. And there you go. Now we're just left with the limit as h approaches 0. Most people don't even have to rewrite this out. I think you can kind of see what's going to happen. But I like to rewrite everything out just so I don't confuse anyone. 6xh plus 3h squared over h. And then what? What do I do now? Because I can't direct substitute. Factor out an h. Good, because everything has an h. So basically, if you take an h out from every single term, you'll be left with, I just canceled out an h from everything, and you'll be left with just the limit as h approaches 0 of 6x plus 3h. And now you can plug 0 in for h, and then you'll obviously just be left with 6x. So once I plug in 0 for h, I'll just be left with 6x plus 3 times 0, because that goes away. So just 6x. So what does that mean? That means that my second derivative, f double prime of x, is just 6x. Okay, that's what that means. So I can pick any x value that I wanted on this graph and find the second derivative by plugging in that x value. It's like a universal derivative. Okay. All right.